Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it's an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside. We are in the final section of Chapter 6 with all the triangle stuff we've been doing, including some things with proofs, including some things with graphs, including some things with compass construction, a lot of theorems involved, a lot of different centers of triangles you've probably never heard of, you'll probably never hear of again, you've probably already forgotten. But we are in section 6.7, where we're looking at inequalities in two triangles. Looks like a short section. I'm looking forward to it, and we'll see what we do. After this, we're going to be looking at some chapter review and chapter 6 tests and cumulative assessment, blah, blah, blah. And then we move to chapter 7, which I don't know what it is, but my guess is we'll include a side and call it quadrilaterals, but we'll find out then. Let's go ahead and look at what we have now with inequalities in two triangles. Start with the lecture portion, and in that lecture portion, only previous, indirect proofs are coming up. I did not know if that was going to happen. Only previous vocabulary is showing up, inequalities, which we just came off of from the last section. The last section had stuff involving, I always forget the name, triangle larger angle theorem, or largest angle and triangle longer side theorem, or whatever they are. All those things that just compare things within a single triangle. But now we're saying what happens if you have two triangles and how you compare them. Let's take a look at how they want to talk about that. You're going to compare measures in triangles, not necessarily with a protractor, but which ones are bigger and smaller, and solving real-life problems using what's called the hinge theorem. I don't know it by name, but we'll go and figure out what it is. Maybe some guy named Hinge. Comparing measures in triangles. Imagine a gate fence between fence posts A and B that has hinge. Okay, I got it. Imagine a gate between fence posts A and B that has hinges at A and swings open at B. So right here, this is the gate, and it can swing open that way, and you can see that A's thing right here, it would stay the same length and just rotate around, kind of like the radius of a circle. Not that radii rotate around, but it goes that distance, like A is a center. As the gate swings open, you can think of triangle ABC with side AC formed by the gate itself, side AB representing the distance between the fence posts, and side BC representing the opening between post B and the outer edge of the gate. So maybe something like that. So this could be your C. So this could be a triangle right here, but this thing could swing open more, and if it's, well, they're going to draw it for us right here. Here is that gate post. It looks a little different on the ground, okay, but here's that gate post, and when it swings open to here, it's an obtuse triangle or a right triangle or something from there. We're looking at it from a different angle. But then when it swings open more, you can see different forms of the triangle, and it can swing beyond. You can see it can swing beyond here, and C could be out here, and this could be your triangle, right, like that. So we can have different kinds of triangles. Well, what are they trying to tell you about this? I want you to think about what they're trying to say. Notice as the gate opens wider, both the measure of angle A and the distance BC increase. This suggests the hinge theorem. So my guess as we're comparing measures in triangles is the distance from A to B doesn't change, the distance from A to C doesn't change, but as we swing it open, we create a new kind of triangle with new angles and a new third side length. Let's see what they want to say about it. The hinge theorem. If two sides of one triangle are congruent, yes, to two sides of another triangle, and the included angle, that means the angle in between, the included angle of the first is larger than the included angle of the second, then the third side of the first is longer than the third side of the second. So what they're saying here is this isn't a side angle side case because only two sides are congruent, and this is why this is not enough to say that triangles can be congruent just by knowing two sides are congruent. If this side is congruent to this side and this side is congruent to this side, you can still manipulate the triangle enough to make two unique kinds of triangles and not the exact same identical one, because that included angle, the side in between them, it can open and close, kind of like a gate, like the hinge of a gate. This V and this R. Open and close, and what it's going to do is it's going to change these triangles kind of drastically. It makes this angle larger, and thus, as we started talking about in the last section, a larger an angle, the longer the side opposite, but when you have these sides the same as these other ones, that's really going to make that side comparatively longer, and of course the angle is longer. Not as a result, the angle is what's made first. The angle is bigger, and the side will be longer. So it's just going to make I don't know if it's always going to be bigger in area, but it's going to make a longer side over there with the triangle. So that's what the hinge theorem is suggesting to us, that a larger angle will mean a longer side when you compare two triangles, that one side will be longer than the other. The converse should kind of say the other way. If two sides of one triangle are congruent to another and the third side is longer, then the angle would be larger from the longer one. So, I just lost everything. So this is congruent to that, This is congruent to that, and then the 12 is bigger than the 9. That'll make the angle C larger than, or measure of angle C larger than measure of angle F right there. So now it's kind of about the distance between the fence and the part, doing all that stuff. And that's what they're pointing at there. So we have the original hinge theorem. Angle larger means longer opposite side compared to the other triangle. This is all about comparing two triangles. And then longer side means larger angle is the converse of the theorem, assuming the two sides are the same. So let's look at an example using the converse of the hinge theorem. Given that segment ST is congruent to segment PR, we can see these two are congruent. How does measure of angle PST compare to measure of angle SPR? PST is right here, and then SPR is right here. I'm not marking them congruent, I'm indicating where they are. Well, they're probably going to talk about these two being the same, given to be congruent, and by reflexive property, we can say these are congruent to each other. So we have two sides that are congruent, but then this side is longer than this one. Therefore, this angle will be bigger than this angle right here. Measure of angle PST bigger than measure of angle SPR. And they're saying all that reflexive property, that's going to be congruent there, but those two sides compare differently. PST is bigger than SPR because the converse of the hinge theorem. Okay, I'm going to move forward and look at using the hinge theorem now. And let's move this thing over as well because my face is so important to this. No, it's so important that I don't cover this. Given that segment JK is congruent to segment JL. Okay, so same thing, and also by the reflexive property, we can say this is congruent. So these two triangles compare so equally in these two ways, but then you have a bigger angle than this one. That'll make the length of segment MJ greater than the length of segment ML by the hinge theorem. And that's what they're stating for all that stuff. JM is greater than LM. They have some more examples there, and of course we'll hit our own problem set. Proving the converse of the hinge theorem. Okay, so they get to prove it for us. We don't have to do a proof for this. Sounds good. So example 3, their proof is two sets of congruent sides. And we know, this is the converse by the way, we know that this is longer than that. It's a given. So how to prove that this angle is bigger than this angle? Let's see how they go. Oh, they use an indirect proof in their proof. So to prove that this is true, first we could prove that that's not true. We could prove that it's not greater, or sorry, we can assume that it's not greater than. If it's not greater than, then AC would be less than DF by the hinge theorem. Okay, then this would be less than that, but that's not the case. Sorry, I'm going to read what they say. If this angle was less than this angle, then AC would be less than DF, because that's how the hinge theorem works. So it sounds like we can use the hinge theorem to talk about the converse. Interesting. I wonder if we get to prove the hinge theorem at all. If it equaled it, then these angles would be equal. So by side angle side, then these two would be the same because of CP/CTC, that two sides would be the same length there. But both conclusions contradict the original statement that AC is bigger than DF. So we can use the hinge theorem to talk about, the hinge theorem would make bigger angles have longer opposite sides, but if it was a smaller angle, it couldn't have a longer opposite side. So that's what contradicts it. Nice, we get to use an indirect proof for that. I wonder if we can choose when to use indirect proofs. I don't know if that always works to do. A paragraph proof for proving triangle relationships. I don't know where we're going with this. I think the point is we can use the hinge theorem in this proof. We have angle W or XWY marked congruent to angle XYW right there. And WZ is greater than YZ. Where's WZ? Right here. They're telling us this is greater than that. It's hard to mark those things. I'm just indicating where they are. And that'll prove that this angle, WXZ, I'll just kind of mark it more, is greater than YXZ. Little guy right there. So let's see what they say. I wonder how the two triangle things will work. Because this angle is congruent to this one, these sides are congruent to each other opposite. Boom is congruent to boom by the converse of the base angles theorem. Another way of that isosceles triangles do that, I guess that's the name of it. We can say converse of the base angles theorem. Someday I'll remember that. By the reflexive property, XZ is congruent to itself. So you have two different, okay, so we're not going to use this angle per se for anything other than to show that there's side lengths. The whole point of this is to find two sets of sides in triangles that are congruent to each other. So in this big triangle and this big triangle, we have these two parts congruent to each other. Boom, boom, and then boom to itself by the reflexive property. But now because this length is greater than that length, by the converse of the hinge theorem, we can say this angle is greater than that angle. So that stuff's making sense. I'll be ready to do those if we have to do proofs as well. Let's look at some real life problem stuff that they're going to talk about that's not a swinging door. Two groups of bikers leave the same camp heading in opposite directions. Each group travels 2 miles, then changes direction, travels 1.2 miles. Do they go straight back? Group A starts due east, then turns 45 degrees north. Group B starts due west and turns 30 degrees toward south. So due east is straight east. Boom. Oh, they show it. And then due west would be straight west like that. And then they talk about the turn north. That lets you go that many degrees in that direction. So that's an example of a 45-degree turn. Which group is farther from the camp? Explain your reasoning. It would really be helpful to draw this diagram. So they have something that shows where you ultimately end up. It's all about kind of where you end up with things, but keeping in mind what? That they traveled the same amount together first before doing their turn. So we go 2 miles here, and then you make a 45-degree turn to go 1.2 miles. 45-degree turn means inside the triangle. Remember, it's the obtuse angle here that matters. That's 135 degrees. It looks like that's something they wrote down below. And then this one with the 30-degree turn over here means inside here is a 150-degree angle. So 2 sets of triangles where you have side lengths of 2 and 1.2, 2 and 1.2, but the included angles are different. This one's bigger than that one. So the farther distance from camp is group B because of the hinge theorem. Because the hinge theorem here, this length is going to be greater than that. So group B is going to be traveling farther. They're farther from the camp. Here's a better drawing for that. Because the included angle for group A is 15 degrees. Okay, so they're just talking more about it. Okay. Hey, all right, that was the lecture portion. Let's go ahead and start looking at the vocabulary and core concept check, and then we'll go straight into the problem set, which I think is up to 24 or 27 problems or something like that. Not a whole lot. Explain why the hinge theorem has that name. Yeah, and that's good, because I not only was not aware of the name of it, didn't know why, but it totally makes sense. Think of a door hinge where the spacing between where the frame width and door width are equal or are fixed, but the angle of rotation from the hinge can change. This can form different triangles with fixed side lengths. I'm gonna get that all out of the way in a second. Side lengths. Okay, so I'm gonna put it like that. So yeah, so it's kind of that idea, and I really like how they do bring that up because it's something we can think about and like really understand. That imagine that there's an actual connection between imagine that there's actually a connection right here that you actually can't see because I'm gonna change the side length of this. So here's a kind of triangle I can make right here, but then when I do this, here's another kind of triangle I can make. I'm increasing this angle down here at the hinge, right, like that, and then this side is increasing right there because I'm increasing the angle, but these sides have stayed the same. My arms aren't growing or shrinking, and so that's kind of a nice way of doing it. Complete the sentence. In triangle ABC and DEF, if AB is congruent to DE, BC is congruent to EF, and AC is less than DF, which measures are what by the converse of the hinge theorem? It's best if you draw these kinds of things. I'm not going to draw them to scale or anything. I just want to know where I am. ABC, DEF, know what corresponds here. So AB is congruent to DE. BC is congruent to EF, and then AC is less than DF. They're talking about the lengths here. This is smaller and this is bigger. If this is bigger, this angle will be bigger right here. Angle E is going to be bigger than angle B. Measure of angle E is greater than measure of angle B by the converse of the hinge theorem. The longer side one will have a greater opposite angle. All right, guys, I'm going to jump into the problem set with that in mind. I wish that was just a normal problem. It seems normal-esque enough. We're going to do numbers 3 to 24 on this, so check out the PDF down below. I'm going to have that one attached. I don't know if we're going to do any graphs. It might make sense to actually do some graphs if they get some same side lengths. Maybe they can do something with slopes. We saw the things with the compass direction stuff, like due north, due east, whatever. So we'll see what we get into, and let's go ahead and get into it. We're going to start right along with problem number 3. Copy and complete the statement with less than, greater than, or equal to based on what you have here and explain your reasoning. So on number 3, let me write that. Measure of angle 1 is blank compared to measure of angle 2. So on number 3, we do have these two diagrams here where we have congruent sides given, and by the reflexive property, these two are going to be congruent as well. Remember, that's a shared side in both of these. But 42 is more than 39, so by the converse of the hinge theorem, opposite the bigger side will be the bigger angle. So angle 1 is going to be greater than angle 2 in comparison. by measure. And that's not a greater than or equal to, by the way. That's just an underscore to show which one it's going to be. That will be number 3. Number 4, these triangles are separate, but they do show which sides are congruent, and the included angles are in between. This is the converse of the hinge theorem again, to compare 1 and 2, where I should just like have a copy and paste thing ready to go for this. Hold on. I'm going to make sure it looks good when I write it first before I do that. So copy. Okay, I'll get ready for number 5 on that one as well. Anyway, 14 is more than 13. Because 14 is more than 13, angle 2 is going to be greater than angle 1. Remember, this whole section is about inequalities in 2 triangles. What's greater than, what's less than, when they're 2 triangles based on the things that are the same that you're able to equally compare. If those side lengths weren't congruent, we couldn't understand that comparison and such. There wouldn't be enough information to conclude anything. Here we do have that. Number 5. Number 5 is an interesting case here because we do have the sets of congruent sides and the included angle is in between right here, the 1 and 2 to compare. However, this third side, unmarked, is that reflexive property congruent to itself scenario. If it's congruent to itself, then you have, by side, guys, we have congruent triangles. And 1 and 2 are corresponding parts. They're congruent to each other as well, so their measures are equal. Opposite the equal sides will be equal angles for 2 triangles that are the same in every other respect. So that's what we're looking at there. That is number 5. And number 6, paste. Don't mind if I do. Number 6, the congruence right here, but 25 is more than 23 by the converse of the hinge theorem. It's interesting how they attack the converses first. Measure of angle 1 will be greater than measure of angle 2. Once more. I don't think there's anything else you have to look at with that. And that's kind of it, and that's all. All right, number 7 through 10. Copy and complete the statement with greater than or less than greater than or equal to. Explain your reasoning. More of the same, but this time it looks like the hinge theorem is at large. So on this number 7, we have a set of congruent sides that are marked, and then in between by the reflexive property, these sides would be congruent to each other. The included angle right here is 36 degrees, 32 degrees respectively. Opposite the larger angle should be the longer side. So AD should be larger, greater than CD in comparison. Okay, number 8. Hopefully this is making sense. I might be over-explaining it even. MN and LK, let me get started writing. As I say, where you have the included angles and the 123 is greater than 114. So we're going to be looking at this length LK right here to be longer than MN. Just based on all that, so LK. Kind of expected that to happen. Are we going to expect an equals here? Likely. I wonder how they're going to present it. Ooh, maybe even here. Never know. Nope, not here. Number 9. I was thinking maybe if these were parallel lines, we could talk about congruent alternate interior angles. I would have loved to see something like that. We have congruent vertical angles here, but that is no matter. We're only looking at the ones that's the included angle, the one between the known congruent sides, and 24 is more than 22. So this UR is going to be more than this TR right here. UR is greater than TR, or TR is less than UR. It's less than UR. And you, where's my circle thing? You believe in yourself there, kiddo. You're on your own, kid. You are greater than you are self. Number 10, AC, DC. Okay, let's see. AC, DC. Included angles here, yeah, and 35 is bigger, therefore AC will be greater than DC. I don't have much to say on that. No equals on any of these ones. No trickery to be had. Oh, this is hinge theorem. Oh, here we go. Okay. Sorry, I was just looking at the rest of the diagram. Okay, let's keep moving forward. Now, number 11 and 12, we do have proofs. Let's see what we can do with these. I will leave the given and proof stuff the way that it is, and I'll mark it up on that diagram. I hope you don't mind that. Let's see what they want. And I don't know if I get to do indirect proofs or what. It says see example 4. I don't know which one that was. We'll try something out and just see how it works. Given xy is congruent to yz. Hold on. All right, and it looks like it's marked as well. Segment XY is congruent to segment YZ. That is given. So already marked. They do mention measure of angle. So I believe in their proofs they were allowed to use these theorems we were talking about. Whoops, not congruent. They proved the converse of the hinge theorem. I think they used the indirect proof for that. They never proved the hinge theorem. Because they're mentioning example 4, I believe we're allowed to use the hinge theorem or the converse of the hinge theorem in this. It doesn't sound like they're telling us to actually prove the hinge theorem. They're just saying make a proof and you can use the theorem within. They're just saying use it. So given. Yeah, there's not much I'm going to say on this one, guys. All we need to do is make sure, remember what the hinge theorem needs to start with conditionally. 2 sets of congruent sides in 2 different triangles, and the included angle for both triangles being comparative, greater than, less than, or equal to. So then we could talk about the other sides. That's all we're doing here. I guess. It doesn't look like we need to say anything else. So my step 3 needs to be, because here's what we need. We need another set of congruent sides here. That's the hinge theorem setup. And this one we can say WY or whatever congruent to itself. So WY is congruent to itself, shared side in both triangles. This is by the reflexive property of congruence. Now that we have the setup that the hinge theorem necessitates, and we've mentioned the givens that are important for this, again, WYZ is greater than WYX. Here's WYZ. I'm just going to kind of call it 1, and here's WYX. I'm going to mark it a little bit littler, I'll call that 2. They're not congruent. This guy's bigger than this. So which one's longer? Right here in the proof. WZ is longer than WX as far as lengths go. Length of segment WZ is greater than length of segment WX. That is by the hinge theorem. And once again, it sounds like we can kind of just use it in this. It doesn't sound like they ever want us to necessarily prove it. I don't know where I'll necessarily go with the proof. You know what? We might have done this proof. I did 6.6, and I believe in section 6.6 there was a question. It never said hinge theorem. There was a question that I think let us do something similar to this that kind of made a proof. I think it was more. Yeah, we might have. I'll have to point to that maybe if I can find and determine if that was a hinge theorem in and of itself, the proof. All right, given this, prove this. So it sounds like here we're going to do the converse of the hinge theorem for this one. Actually can go pretty fast. Let me just kind of copy the statements reasons thing because sometimes that's the stuff that takes longest to write. So, and then I'll kind of erase anything else that I shouldn't use or keep, which is everything else. But it might just be another 4-step proof, another reflexive property thing. Looks like it's coming in the way because what we do need are the 2 sets of congruent sides and then whatever else is being marked alongside it. So in this one here, 12, step 1, segment BC is congruent to DA. That's already marked. Probably should have kept the givens up. Given. And then DC is also less than AB. I should probably leave that given for last. I should probably do this other side here and then mention not the included angles, but this is the situation for which we want to compare those angles. So this time I'm going to say AC is congruent to CA. Now, that's the reflexive property, but you might be wondering why I wrote one of them as AC and the other as CA. Whereas last time, I kept them the same, WY and WY. Because despite the fact that triangles aren't congruent, so parts don't truly correspond, they are looking to compare things in a corresponding manner, and this is more of a rotation. How do I do this? Instead of a reflection of 2 objects, it's more a rotation of 2 objects, like that. So I can't do this. There we go. Instead of reflection, it's more of a rotation of 2 objects like that. And so now when parts compare, AC in this triangle compares with CA in that triangle because of the way that we have that comparison. Case in point, Remember when we had angles 1 and 2 to compare with here? Now when we're comparing BCA and DAC, well, BCA is right here and DAC is right here because it's not more of a reflection of these objects. And again, it's never a true reflection because they're not congruent, but it's more of a rotation of these objects. So now we're going to compare these two angles and which one's bigger based on showing that DC is less than AB. I'm going to make AB the bigger guy and call that, I guess, 1. And then this guy 2 just to show you where they are. So we have the situation that can indicate us that we can use the hinge theorem, or the converse of the hinge theorem rather. Two sets of congruent sides comparing the we're going to compare the measures of the included angles using a proof by knowing that this side is longer than that side. If AB is longer than DC, then measure of angle BCA is going to be greater than measure of angle DAC. And that's what we're going to say by the converse of the hinge theorem. AC, converse of hinge theorem. All right. Not used to doing 4-step proofs with you guys. If you've seen me do some others, they've generally been a lot longer than that. So as long as I can use those theorems, we are good. Excuse me. Is this a indirect? No, this is probably one of those word problem things. In exercises 13 and 14, you and your friend, let me hiccups. Give me a second. I'm holding my breath after drinking water. Hopefully that's good enough. Okay. No hiccups. In exercises 13 and 14, you and your friend leave on different flights from the same airport. Determine which flight is farther from the airport. Explain your reasoning. Okay, your flight, you fly 100 miles due west, and then it turns 20 degrees toward north and flies 50 miles. So as far as these drawings go, because if you were here for my lecture portion, you can kind of see, let's say that this is the airport, and then here, I'm going to fly west this way 100 miles. Like that. And then I'm going to turn 20 degrees due north. That means like 90 degrees due north would be like that. 20 degrees due north is going that direction like that. And it's going to fly another 50 miles in that direction that we swing that 20 degrees. So here's that 20 degree turn where we go another 50 miles. Like that. The only problem with where I'm labeling 50 right now is I'm going to close in this triangle. Close this in as a triangle, I should say. So it's going to be looking like that. Now the 50 is just taken up. It's just got clobbered. So I'm probably going to change the 20 somehow. Let me do this. So 50, I'm going to write right here. And then the 20 degrees is 20 degrees like that. So there's a triangle. Now what's the whole triangle about? This path, let me kind of shrink that. This is my distance from the airport right now. Now, I'm not going to, this isn't Pythagorean theorem, but I'm not going to use like trig or something and tell you what that distance is. We're going to compare distances, not how long they are, just which one's longer, using the hinge theorem. Now, there's more I'm going to have to say about that in a second. Your friend's flight, 100 miles due north. Okay, so we're going this way. 100, though, that's the same number. So think of that hinge, whoop, swinging open like that. 100 miles. Actually, that's not even the hinge we're talking about. 30 degrees, turn 30 degrees toward east. So here, instead of 90 degrees east, we're just going to go 30 that way. So 30 degrees east to go the same 50 miles as like I did before. So 30 degrees and 50 miles out that way. Okay. So with that in mind, there's then this distance from the airport. Like that. That obviously doesn't look the same as far as whatever. It's just the idea of the drawing. Which flight is farther from the airport? Okay, so what we need to do, the 20 and 30 are not inside the triangle, but this swing, remember this is a linear pair with what is inside the triangle. What is inside the triangle is 160 degrees because it's supplementary with the 20. 180 minus 20 is 160. That would make this one 150 degrees here. So given that we have the same, again, 150, 150, doesn't mean 150 miles, it means 150 separately. Given those things being the same, the thing to compare is the angle, the included angle right here, and this angle, this is my flight, this angle is greater overall. Basically, I have flown straighter overall, so I'm probably distancing myself from the airport more. In that case, that would be me. So because this is your flight, I am farther from the airport because my included angle is greater than my friend's included angle. Basically, that angle of rotation. My angle, actually, here, I take it back. My angle of rotation was less, but my angle in my triangle is greater by the hinge theorem. The distance of the side opposite the angle is greater in my triangle. All right, there we go. I probably don't have to write that much in general, just hinge theorem. That's the reason. But my angle is greater in the triangle. All right, number 14, my flight, my friend's flight. I guess my friend probably gets to have a farther flight than me this time. So number 14, flight. My flight flies 210 miles due south. Where's the friend? Other friend's gonna go north, so I'm gonna go this A. So 210 miles due south, like here. Then turns west. So 210 miles. Turns 70 degrees toward west. So once again, instead of 90, we'll go like that. So this will be 70 degrees toward west to go another 80 miles. Okay? So now my flight distance is this. This is how far I am from the airport, like that. Again, not trying to get actual numbers. That's me. My friend went 80 miles due north. So this is going to be interesting to look at. Oops. Because of the parts that compare. It's really still about the included angle, though. But you've got to look at these turns. So 80 miles due north. And then 50 degrees toward east. He turns. So 90. It's about halfway, a little more than halfway there. So 50 degrees toward east. And then travels this is the 200 mile travel here. Travels 200 miles, 210 miles, I should say, right there. All right, those are the drawings. So let's go ahead and connect that guy. Okay, who traveled farther? Well, let's talk about those angles that are inside once again. If this is 70 degrees, its supplement is 110 degrees, and this 50 degrees, its supplement is 130 degrees. So it's really just all about the bigger angle, guys. These here's 80, here's 80, here's 210, here's 210. So we have that side comparison, and the included angles are the ones we're talking about there. Therefore, the bigger angle on the inside is the one that can show which distance is farther on the outside. Your friend's flight took him farther from the airport this time. Friend's flight is farther. Because of the bigger included angle and the hinge theorem. Basically, I'm just going to keep it short this time. But it's all hinge theorem based, y'all. All right, let's keep going. Number 15, error analysis. Oh, what mistake did we make this time, and how can we correct it? Here we go. Describe and correct the error in using the hinge theorem. So let's look at what they said. We have sets of sides right there that are congruent. I don't know if their problem is they didn't mention reflexive property or something, but let's see. By the hinge theorem, PQ is less than SR. So here's PQ, here's SR. Now, opposite of PQ is this angle 58, and opposite the SR is the angle 54. Well, 58 is more than 54, so PQ should be greater than SR. Now, they didn't bring up the reflexive property. I guess we're good in not having to, not requiring that. Okay. So let's forgive that part. The problem is PQ isn't less than SR. It's greater than SR. This is because the included angle between, which is all it means, the included angle between the two congruent sides, sets of congruent sides, is larger. Well, the measure of the included angle is larger opposite PQ than it is SR. Right? 58 degrees versus 54 degrees. So that's the comparison. So PQ is greater than SR is the correction. That's by the Hinge theorem. That's number 15. Okay, let's look at number 16. Which is a possible measure for angle JKM? Select all that apply. So 16. I'm really doing a lot less copying down problems on my side if I can just use the things on this side. I hope that's okay, because a lot of triangle diagrams do a lot to me. Instead I need to really mark it up right. JKM is right here. Now they show a 25-degree angle measure here, with this being 8. And again, there's a reflexive property shared side thing right here of congruency. So these two are congruent. Excuse me. These are two sets of congruent sides when we're looking at the included angles. 8 gives us 25 degrees here. 6 is going to give us a smaller angle here with everything else that compares the same. So we can't have anything that's 25 or more. It must be less than. Do we know exactly? Nah. Things can change all depending on how they change it. So it's got to be 15 or 22. So which is the possible measure? Select all that apply. 15, yes. 22, yes. 25, no. 35, no. Now, one thing we haven't really brought up yet together. Oh, never mind. Never mind. Forget what I was going to say. Actually, I want to think about it again. Nope. Forget what I was going to say. Okay. Number 17. Oh, sorry. A and B. 15 degrees and 22 degrees. Okay, number 17. The path from E to F is longer than the path from E to D. I want to find a way to do that. I'm going to say I'm going to have 2 big congruent tick marks versus this one. Sorry about that. The path from G to D is the same length. So I'm going to do 3 congruent marks here. Path from G to D is the same length as the path from G to F. And of course, by the reflexive property, this guy here. So they said E to F was bigger, right? Yeah, longer. So the 2 congruent tick marks is going to help me with that. What can you conclude about the angles of the paths? Explain your reasoning. Well, they're not telling us which ones to compare, so we're going to figure out which ones we want to compare here. And the ones we want to compare are the ones opposite the sides that are different, which is comparing this one and this one. No, I'm not making them the same. I'm just showing which ones you want to do. EF is bigger than DE. We got congruent sides from these, congruent sides from these guys, so here are the included angles. If EF is bigger than DE, then EF's angle G is bigger than DE's angle G. We don't just call them angle G. I'm just saying that that's the ones we're going to compare. So we can conclude that measure of angle, this is going to be EGF. EGF is greater than the measure of angle EGD. Ultimately, this is by the converse of the Hinge theorem. By the converse of the Hinge theorem, I feel like I should capitalize the C here. By the converse of the Hinge theorem, that might be enough to say, but EF is greater than EG, so its side opposite, its angle opposite, will also be larger in the 2 triangles with 2 known congruent sets of sides. I mean, this is probably one of those things that I don't know if I need to say all this stuff. It's kind of like, I don't know how often you've gotten to use Pythagorean theorem so far, but I don't say, by the Pythagorean theorem, the right triangle's legs are the hypotenuse, and when I do square the sides of the things, and here's the proof of the theorem. I don't think I have to say all that every time. I don't know, but it's not meant for you to write all that. It's meant for me to teach you why the converse of the Hinge theorem is acceptable as a reason, or what it's saying. All right, number 18, abstract reasoning. In triangle EFG, the bisector of angle F intersects the bisector of angle G at point H. Ooh, that sounds like incenters. Sounds like an incenter where they intersect. So we probably get to practice this. Let's see. I don't know how I want to draw this. Let's do it like that. Okay, let's call it EFG. Sorry that it's made to look isosceles. That I don't really think that matters. The bisector of angle F, that should be easy enough to do. Just go straight down because the way that I drew it. Intersects, so here. So these are congruent. When I mark these guys, those are congruent marks. Intersects with the bisector of angle G. Let's do our best to, that is terrible. Not our best. Let's do our best to do some form of some bisector. Sure. At point H. So H is an incenter, y'all. Angle bisectors are concurrent at the incenter. We'll talk more about that if they want us to do something with it. Let's see what they want us to do. Explain why FG must be longer than FH or HG. Where is FG? FG must be longer than FH or HG. Oh man, I thought we were going to talk about incenters. The bisector of angle F intersects the bisector of angle G at point H. Explain why FG must be longer than FH or HG. Maybe we do get to do an incenter thing. So I'm curious to do this. The only thing I want to talk about is how these lengths will be the same, right? If it was a good-looking bisector or incenter. I'm guessing it would probably go a little more up here to be a good incenter. The distances that are equal with an incenter are the altitudes to these other sides. Like, say, like this is the same length as that and is the same length as that. So these are all the same. Now, I feel like those would be used in some sort of way to talk about things. I don't really know what yet. I wanted to talk about these being in different triangles. Now, suddenly, I'm not too certain that that's what I want to do, but let's go and take a look at them anyway, just in case. So the bisector of angle F intersects the bisector of angle G at point H. Explain why FG, I'll erase those incenters if they have the things if they have nothing to do with incenter, must be longer than FH or HG. I mean, I feel like it just must be just because. I'm trying to think what this has to do with hinge theorem. I'm sorry. I'm trying to think what it has to do with hinge theorem. Maybe it doesn't. Maybe it's just more the triangle inequality theorem. FG. You know what I don't like is this is me deflecting right now. You know what I like is they shouldn't have these bars up here. It should say the length of. It's the side of a triangle. I mean, but that's not something that would tell you why. Come on. I know this. What do I want to say? Is this a hinge theorem thing that I'm not seeing? Or is this an incenter thing that I have to see? Okay. So this, I'm curious if they're talking about only one triangle or not. I think that's where I'm having most concern, because the next thing I'm thinking about is maybe they're talking about two triangles. Because right now they're just saying why this has to be longer than this or that. Oh. Okay. Okay, they're not talking about hinge theorem. I shouldn't be thinking in that context. Okay, this is more of a 6-6 thing. Okay, yes, they're only thinking in terms of one triangle. And what we should be aware of in a case of this thing, I mean, we might have to kind of explain a little bit. I'm not really all that sure. We can explain quite a bit here, and I'll try and do my best with it. But basically, it's the triangle longer side theorem or larger angle theorem or what have you. We got to conclude that this angle is bigger excuse me, that this angle is bigger than these two angles, therefore the side opposite is bigger. But I don't know what this has to do with hinge theorem stuff. I'm going to go ahead and say it doesn't, because we're not talking about two triangles, really, because we don't have sets of congruent sides there. Sorry about all that. Okay, so here we go. We're really looking at how measure of angle HFG is bigger. So measure of angle, I'm just going to write it like this, FHG is the greatest angle in the triangle. Now, here's why. Because it is the sum of the measures of the other two angles in the triangle. Now, you might not have known that. I'm typing this out first. Here's the thing. I think the in-center thing does, well, I don't know if the in-center thing helps us, but me drawing this altitude kind of helped me recognize what we have here. And these two right triangles, this angle is complementary with this one, which means they add to 90. And this angle, actually, maybe I'm saying that part wrong. I don't know that this angle is the opposite of that one. But it is the sum. Darn it. Hold on. I want to pause this and be right. Again, let me think about it. Okay, so I was on pause with this one for a second. I feel like this problem's ambitious. Now, what I said was not correct as far as the things being what they're, but I do think it has to do with in-centers. I think it has to do with in-centers, and I think it has to do with the hinge theorem, but I don't think it has to do with in-centers in this way, that we need these, because I don't think I need right triangles. So, but I wanted to make that statement. What I do think this will have to do with, though, is the hinge. The hinge theorem, because we're in that section. Now here's something else that we know about here. Let me get rid of this green here. I know this is a triangle, but let's talk through this. So we have angle bisectors here. Now we know that these ones are concurrent to it. What I didn't mention, here's why I think it has to do with in-centers. I think that we can mention that a third angle bisector would also be able to go through this, right? That's the whole thing about in-centers, is the angle bisectors are all concurrent to each other. So these ones would be congruent as well. Now, the reason why I want to, bring those up is because I think the angle bisectors also they play a role in this. I just don't know where. My thought to this is, because when I was looking at this right triangle, so basically here's what I was doing. When I was on pause, and when I was looking at this triangle that I had drawn here, I was like, well, I got this smaller triangle here, but then I was looking at this. My triangle's different than what any other random triangle would be drawn. But I was like, then I'm looking at this right triangle here and saying how something like that can compare. The fact to have an angle bisector means it's going to be like half the size. And so I really want to compare how those things work and look at the bigger triangle in essence. Like the three big angles, if you add them all together, measure of angle FEG, EFG, or EGF, and measure of angle GFE, those would all add to 180. That's true in any triangle. However, if you divide, because we have bisectors, if you divide some of these ones by 2, if you have the bisectors, then you can divide them in half, then you can get something that goes to 90, which is nice because then we could look inside that triangle. This triangle right here, let's go back and draw that. Inside this triangle right here, you know that if the three angles in the triangle add to 180, but 2 of them get divided in half, then those 2 would have to add to 90? If they add, no, that's not true. No, because then there's a third angle. So HFG, I got HGF. Honestly, I'm struggling with the problem. I'm struggling with the problem. I'm struggling with this problem, guys. Couldn't tell you. Something I'd love to go back to later. I'm sure there might be a key thing for this as well. I know I want to do something. I want to do something with that hinge theorem, y'all. Totally. I don't know if I got this one in the cards. Let me pause and think about it one more time. Then I'll go to it. Okay, I think I made my decision on the problem. So the three big angles add to 180. Boom, boom, boom. It's true for any triangle. These three add to 180. These three add to 180, whatever like that. But because these three add to 180, and because we have angle bisectors, if we do divide them in half, then we can look at any sets of the angles that do divide in half from any of these sets, like this one, and then you have to choose one of these two. It doesn't matter. I'll just go and choose this one. So three of those that are divided in half would add to 90. Now, the reason I want to bring up 90 is because 90 is half of 180. The whole thing, I decided I'm not going to use the hinge theorem on this, but I want to use the triangle inequality theorem. I want to show that this is the biggest angle, basically. I want to show this is the biggest angle, but not from the reason I said before. Okay, three of those add to 180. That's fantastic. But what I really want to do more of is have three bisected angles add to 90. So let's choose one from this one. Let's do the one, I want to do the ones inside the triangle if I can. So measure of angle HFG. And then let's add this one, measure of angle, I guess HGF, measure of angle HGF, and then we need one of the angles from this one here. Measure of angle HEF or whatever, or HEF. So that would be 90 degrees because that's half of the angles here. All these ones got bisected. What's important about these adding to 90 is that these two, the ones that are inside that green triangle, have to be therefore less than 90 because this one has to have some sort of measure. So when I subtract that over, when I get this out of the way, that means measure of angle HFG plus measure of angle HGF has to be less than 90. Has to be less than 90 degrees. But since these three have to add to 180 now, HFG, HGF, and FHG, you know, this one right here, since those three have to add to 180 in the green triangle, measure of angle HFG plus measure of angle HGF plus measure of angle FHG, those have to equal 180, but if these ones are less than 90, that means that this one must be greater than 90 if I subtract the less than 90 amount over. So that has to be greater than 90. If that's greater than 90, like how obtuse this one's looking, and now mine was just some random triangle that I drew, but because this one's greater than 90 and these together added are less than 90, never mind the fact that they're less than 90 alone, that these two added are less than 90, then FHG, being an obtuse angle in a triangle, is going to be greater than either of those. So measure of angle FHG, the big guy, the one opposite this thing, it's going to be greater than measure of angle HFG. And measure of angle FHG is also going to be greater than measure of angle HGF. And in these two, we're going to make two different conclusions here. The ones that they want us to conclude, I think, that FG must be longer than FH or HG. FHG is greater than HFG. So this guy is greater than HFG. HFG is right here. So that must mean that FG is bigger than HG. FG is greater than HG. And now the other one, FHG is bigger than HGF, therefore FG is greater than FH. FG is greater than FH, like that. So those are the conclusions I make with that. Wow. Okay. Well, anyway, so that was the triangle inequality, not the inequality theorem, excuse me, the larger angle theorem one that says the larger angle in a triangle should have the side opposite that's larger. So it didn't use the other thing. I had a bunch of problems with that, trying to decide how we're using in-centers. They didn't really use in-centers outside of knowing all angle bisectors would line up. And I don't know if that's the best way to do that problem. That one threw me in for a loop. When I thought this was going to be a short thing, I got stuck. Admittedly, I hope no one has to watch this part of the video to know that I got stuck on it, because now I'm intimidated by any other problem after this. I just did 18. Here's another abstract reasoning with 19. I'm probably going to have to do the same kind of thing. So we're going to see where we're going to have to go with this one as well. These are going to be a little, they're going to be a little tricky. So number 19, NR is a median. Ooh, this is a centroid kind of thing. NR is a median of triangle NPQ, and NQ is greater than NP. Explain why angle NRQ is obtuse. All right, let's do another triangle. Let's see if we can attack this one with flying color or not. I don't know. Honestly, I have no idea what it said. I just read it. I have no idea what it said until, PQ, until I draw it. That's my motto. When in doubt, draw it out. All right, NR is a median of NPQ, excuse me. So R is going to be a midpoint right here that's dividing these into congruent parts, okay? So then we're doing this. This one looks a little more hinge theorem-like because now what I have is, and remember, we don't know what's isosceles, scaling, and stuff like that, but we do know those parts are congruent, and we know that here this thing can be congruent to itself. That's great. Now they're talking about why NRQ is obtuse of this triangle. Oh, and NQ, this is just straight up converse of hinge theorem here. So NQ is greater than NP, okay? So if I were to, I'll give this like a bunch more tick marks, and this one's just going to have one less. Okay, a bunch more tick marks here than that one. All right, this one's bigger than this one. Why is this obtuse? Okay, so this is a lot of the converse of the hinge theorem, okay? So because NR is a median, NR bisects PQ, and therefore PQ is equal to QR. I can probably put all the congruence and things like that in a bit. I just want to get these things set up. So that's why I mark these two congruent, because it's a median. NR is congruent to itself. They never said prove it, but I'm setting things up by the reflexive property. And by the converse of the hinge theorem, hunge. And I know I'm going back and forth on what I'm typing, what I'm doing. Basically, because NQ is bigger than NP, measure of angle NRQ is bigger than measure of angle NRP. Now, they didn't say, how do we know that one's bigger? They said, how do they know it's obtuse? Angle NRQ and NRP form a linear pair. Right? They're angles that were formed from this median, but they were a straight angle before. I mean, they were the side of a triangle. It was a straight line. They were a straight angle before, and are supplementary. The bigger angle in a linear pair must always be obtuse. I mean, think about that part, right? It must always be obtuse. I'm not going to type that part out. If a linear pair, two angles that add to 180, were equal, they'd both be 90. I don't know how to do this. They'd both be 90 degrees. If you tilt the scales one way, one's going to be acute, one's going to be obtuse. Which one's going to be obtuse? The bigger one. Or which one's going to be bigger? The obtuse one. So that's how we're going to do that, and I'm sure I could do a lot of markings with this. But that's kind of my explanation on that. That was a lot easier to go with. This is a median, this bisects this, and therefore these are congruent. And then these are all lengths right here, and I'm good the rest of the way. Okay, that's my number 19, and that's my story. I'm sticking with it. 18 was tricky, man. Number 20 and 21. Write and solve an inequality for the possible values of x. I'm going to copy this one down. It looks like a lot to take in. All right. So number 20, we have a 3 and a 3 here. So these are congruent, and by the reflexive property, this thing's congruent to itself. So the problem with that, though, is that I don't know what this angle measure is, and we're not comparing that. Well, we have to find a way to... Oh, 27, 102. Okay. If this is 27 and this is 102... 102 plus 27 plus, equals 129, and 180 minus 129 equals 51. Okay, the important part about this is I need this 51 degree angle measure, because this needs to compare to the 110. This needs to compare to 110. The reason is because it's the included angle we have to compare. Here's a side that's congruent to this side, a side congruent to this side. It's the included angles that we have to talk about. Now, 110 is definitely bigger than 51. Therefore, 3x plus 2 is definitely bigger than x plus 3. So when they say possible values of x, we're going to write an inequality. 3x plus 2 is greater than x plus 3. If I subtract x from both sides, I get 2x. If I subtract 2 from both sides, I get 1. 2x is greater than 1. Divide both sides by 2. You have to say x is greater than 1/2. The values of x that would make this true are x values that are greater than 1/2. 1 is greater than 1/2. 20 is greater than 1/2. Things like that. So as long as it's greater than, we're good to go on that. If it was less than 1/2, it's really hard to kind of get a lot of those. But if it was less than 1/2, it would not satisfy the hinge theorem or the concept of what these triangles could be with those angle measures. Now, is it only greater than 1/2? I don't know if x equals 1 will make it work perfectly. I have no idea. We just know that it has to be to satisfy that. All right, number 21. Given B is the midpoint of segment AC, and they marked that thing up for us to kind of show there's congruency. And then they give you something else as well. They show you that segment DC is also congruent in that way. So let's see what to do on 21. I'm going to copy it over, and I'm going to write that down. Number 21. We're almost done. 24 is the last one. So we have congruence here and here, and then, you know, reflexive property would say this is congruent here. So all that's important here is because these two are the same. If this is 2x, I can express this as 2x right now as well. So what we want to do is, you know, once again, we have sets of congruent sides here, sets of congruent sides there. It's the included angles that we have to compare, this and that. No, they're not the same. These are the ones that I'm comparing. Comparing them to these guys from that. Now, there's probably also something else I got to look at, though, because what we don't see is which one's bigger. How do we know that 4x minus 3 is bigger than 2x just based on looking at this? The only way of knowing that it's bigger is by understanding the concept that this side, if this side is the same length as the grounded side, once you turn up on a side, you're going to reach that less than the other side. I don't know if, it doesn't ask me to explain, and I wonder if there's something I should say to make best sense of that. But I know 4x plus 3 has to be bigger than 2x. Not just by, it's drawn that way. It's drawn that way. But I'm sure I can use an isosceles triangle trick to talk about that, because this is an isosceles. Those are the same. Therefore, this has to be, there's something I could probably do that. But this has to be bigger than 2x for that to be true. This is supposed to be a bigger angle. Okay. Anyway, let's solve. Subtract 2x from both sides. Add 3 to both sides. Divide both sides by 2. You get x is greater than 3/2. It's kind of weird numbers that they're going for with all these fractions, and they're kind of small numbers, but that'll be it. And I guess we're not comparing the two angles. I guess the angles are comparing the two sides. Somewhere, somehow, I should be able to say something about that angle being smaller, this side being comparatively smaller than that one. How? I still don't know what I should say on that. Okay, let's keep going. Number 22. How do you see it? In the diagram, triangles are formed by the locations of the players on the basketball court. The dashed lines represent the possible paths of the basketball as the players pass. So A, B, C, and D are players, and then they pass at these distances. A can go to D. It looks like D doesn't go to B, but A goes to D, D goes to C, C goes to B, and A can go to C, etc. How does the measure of angle ACB compare with the measure of angle ACD? Now, I don't have to explain. I can, I just don't have to type anything. ACB is here. ACD is here. How do they compare with what we know? We know these are 26 together. Those are the same. This is 21 to itself. That's the same. We just got to compare 28 and 22. So they're not doing anything specific. Here's point E. The center is just like, I got to stay outside the key. Otherwise, it's 3 in the key. I guess C. It's got to get out of the key as well. Anyway, 28's more than 22. So this guy's going to be bigger based on all these things being the same. So how do they compare? Yeah, let's just write it out. Just the answer. Or I'll just say 28 feet is greater than 22 feet. No, not 28. 22. AD is greater than AB. Therefore, with everything else that we know, that's true. AC is equal to itself. All that by the converse of the hinge theorem. Measure of angle ACB is less than measure of angle ACD. I should probably do it the other way. Measure of angle ACD is greater than measure of angle ACB. Okay. All right, 2 more. Number 23. Uh-oh, critical thinking. Jeez, man. Didn't we decide that critical thinking was open-ended questions? Which ones did we say were open-ended? In triangle ABC, the altitudes from B and C meet at point D, orthocenter. And measure of angle BAC is greater than measure of angle BDC. Oh, thought-provoking, excuse me. I'm looking down below. I think thought-provoking was the open-ended ones. Sorry about that. Anyway, what is true about triangle ABC? Justify your answer. Well, I drew it. So here's ABC. Let's draw an altitude from B to this. In this case, I get to go straight down. Oh, joy. So there's an altitude. I'm going to draw an altitude from C. Probably there-esque. These meet at what? D. And measure of angle BAC and BD. Where's BDC? Okay, I want to put the D over here. All right, so here's BDC. Here's BAC. And goodness, they said that this one's greater than that one. That means my drawing, it will not be up to snuff. Is that possible to be to BAC's? Oh, it must be an obtuse triangle. I was gonna say, so check this out. How can A go inward more? I mean, A is going inward more than D. How could A be a bigger angle for that to happen? The only way for this to be possible is if D is outside the triangle to bend back in somehow, and if A was obtuse in the matter. Yeah. So this is not a good drawing. It's not that this is not a good drawing. This helps recognize that this ain't it. So, see that? Nope. You can't draw it like that. Let's do I have an obtuse triangle? I had this the whole time. I must have used that in the past. I didn't know, but I used that the whole time. Let's do that again, but let's make A the obtuse angle. A, B, C. Now, how do I draw altitudes for B and C this time? You need to extend these sides kind of outward, like this. Extend that side outward and draw an altitude there. Extend its side and draw an altitude there. Because, yeah, the longer angle, if you will, the angle that's farther out needs to be more acute in this case. Here's going to be, there's the altitude for B. Here's the altitude for C. And B and C meet at D with their altitudes. So again, altitudes are perpendicular there and perpendicular there. Here's D. So this is orthocenter based-esque, but here's angle A, here's angle D. In order for D to be smaller, it needs to be farther out than A, if that makes sense, because A's angle to B to C needs to be there. So that kind of reasons with it better as to why that would happen. So justify my answer. It's based on the drawing here. But, you know, once again, if you're meeting to B and C, A needs to be closer to B and C for that to happen. I wonder if that's a way of saying converse of hinge theorem. They share the side length, BC. They don't seem to share another side length, clearly, so I guess not. But anyway, what is true about triangle ABC? Two things. One, triangle ABC is an obtuse triangle. Two, A is the obtuse angle. My justification is just kind of in the drawing there. If it was a right angle, A and D would be the same angle measure. They'd be 90 degrees. That's where the orthocenter would be. The orthocenter must be outside the triangle. The orthocenter must be outside the triangle to form a smaller angle toward B and C for D. Okay. All right, I got one more problem here. Number 24. The postulates and theorems you have learned represent Euclidean geometry. See, to think about, man, all these guys come up with this, and back in the BC days, not Euclid. Wait, I forget when Euclid was, but they discovered this for us, so we don't have to. I mean, in spherical, we did spherical geometry once. I think I had a problem with that question. In spherical geometry, all points are on the surface of a sphere. We did look at this stuff. A line is on the circle. I forget. I think I had trouble understanding what they were saying. So let's see what I can do with this. And the hardest part is just drawing a sphere. Let me get one from Google Images. I'm just gonna type sphere so you guys can see it better and visualize what we're looking at a little bit more. One that's not too obtrusive but makes a little bit of sense. I want it hollow but not complex. I don't know if I can get something like that. Let's just use. Let's see if this one works for us, for our needs. Thank you, BYJUs. Bijus. I don't know if that'll work or not. Anyway, in spherical geometry, all points are on the surface of a sphere. A line is a circle on the sphere whose diameter is equal to the diameter of the sphere. So basically this. So it's already drawn. This is rotating around that disk right there. That's a line. That's a line. In spherical geometry, state an inequality involving the sum of the angles of a triangle. Find a formula for the area of a triangle in spherical geometry. In spherical geometry, state an inequality involving the sum of the angles of a triangle. State an inequality involving the sum of the angles of a triangle. What, like that? What are they asking us to do here? In spherical geometry, state an inequality involving the sum of the angles of a triangle. I have no idea where they're going with this. Let me think about this. Angles of a triangle. I mean, we know that they have to add to 180, right? Angles in a triangle. But they said in spherical geometry. Well, they're mentioning a line. So this circle thing being a line, do they mean if you unfold it, you do something like that? I have no idea. This is one of those things where I just have no idea what the heck they're talking about. Because I don't know what they're doing when they bring that up. Okay, here, let me try it again. All points are on the surface of a sphere. A line is a circle on the sphere whose diameter is equal to the diameter of the sphere. Got it. In spherical geometry, state an inequality involving the sum of the angles of a triangle. I guess what they mean by... My confusion is if they're saying that they said a line is a circle, and by that it means if you unraveled it, then it would open everything up. So I don't have a ball with me here, which is ironic. I'm a softball coach. I should just have them everywhere. But if I wrapped a string around a balloon or a ball, whatever, and I drew a triangle, now if I open up that string, the triangle's angles open up more. Because they said write an inequality. So maybe what they're saying is the angles are greater than 180. I don't really know if that's what they're referring to in that kind of instance. But if they're greater than 180, guys, I have no idea. And you know what? That's something to ask your math teacher. Hopefully they can do it for you. Because listen, I don't do things on spherical geometry. Apologies on that one. If you know more than I do, there's probably an answer key for this stuff online, guys. My solution guide things are meant to help you for the ones you're being assigned for. If you were being assigned this one, sorry, this is one I'm just going to give up on now. Spherical geometry got the better of me. I feel bad about that too. But hey, guys, integrated math 2 can stump. a lowly teacher like myself. Guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. I hope that you weren't trying to look for that one. Or number 18 I got hung up on, but I think I got that one right as well. And I think I spoke through it to make sense of it best myself. Thank you so much for watching. If you want to check out some more, just check the playlist down below and check the timestamps for everything that we were doing here as well. Take care. I will see you in the next one.